Hello, my name is Marco Lisi. I work for the European Space Agency. Today I will speak about the satellite link budget. Now I want to say something more because it would look very simple. Everything is very simple. I am simplifying it. I said that we are not taking into account specifically for a satellite link budget. There are many factors to be taken into account. Just to take an example, the distance between transmitter and receiver. Let's suppose that we said the transmitter is the satellite itself, is the transmitting end of the satellite payload, and the receiver is the ground station end. So it's a user station, a ground station that is on the surface of the Earth. Well, this distance will depend on many factors. The first factor, the most important factor, if you want, is the orbit of the satellite. Because satellites can be on over many different types of orbits that are different in geometry and different in distance from the Earth. But even if you define a certain orbit, for instance, a very common orbit is the geostationary orbit, that again you can get more details about from courses that are on Space Challenges website. And you see that this distance that in a satellite link is usually defined as a slant range depends very much, having frozen the orbit, from the position of the user, of the ground station. So usually, and we will use also this approximation just to make quick and dirty calculations, just to give you an idea of the magnitude of the problem. Usually you say the geostationary satellite is about 36,000 kilometers from the surface of the Earth, but this is true, in fact, only in one point, that is called the sub-satellite point for the geostationary orbit, that is along the equator. But if you are at a different latitude, or even at a different longitude from the longitude of the corresponding to the geostationary satellite position, you would experience a different distance and a different slant range. In the slide, I show the case where, being at the longitude of the geostationary satellite, if I am at sub-satellite point, I am close to the 36,000 kilometers, but if I am at the limit of coverage of a geostationary satellite, so closer to one of the poles, in this case to the North Pole in the slide, then I experience a distance that is almost 42,000 kilometers, so a difference of 7,000 kilometers that is not at all negligible. So there are many factors that have to be taken into account, of course, but the principle is the same. The R in the formula that we have found, the formula of the free space path loss, has to be the R, the exact R, that depends on the position of the ground station and depends on the orbit. So on a case-by-case basis. Let's think about another common case of orbit instead of the sun-synchronous orbits used, for instance, by Earth remote sensing satellites. Those are, the satellite is going around the Earth over an elliptic orbit at an altitude that is around 600 to 700 kilometers. So you understand that the difference between 700 kilometers and 36,000 kilometers is huge. And to this difference will correspond a difference in free space path loss. So the link has to be calculated depending on the actual situation of the link itself, so the satellite that we are considering, the orbit of the satellite, the user station, and so on. But the formulas are valid, are very general. So we can now summarize all our findings, first of all, going into decibels. I have anticipated saying that in most cases in our link calculations, we use decibels. What are decibels? Are 10 log base 10 of the quantity itself. It's a way to express a certain quantity with some advantages. And the advantages are fundamentally two. One comes from the definition of logarithm and the properties of logarithm, And it is the reason why logarithms were invented, in fact. That if I have a complex calculation in terms of multiplications and ratios, since the logarithm of a product is the sum of the logarithms of the factors, and the logarithm of a ratio is the difference of the logarithms of the individual elements of the ratio, you see that it can be convenient really to get back to the budget of the housewife budget we mentioned at the beginning of the course, of the lecture. It can be convenient to go into logarithms representation of the quantities, because all our multiplication and ratios are transformed into additions and subtractions. This is one advantage. The other advantage is that the quantities we are considering are either very, very big, huge, or very, very small. And if we had to consider linear quantities, we would have to deal with trillions or thousands of trillions or trillions of trillions, and quantities very, very small. It's very inconvenient with expressing them in logarithms, in logarithmic form. We handle numbers that look smaller, well, in fact, representing the same big quantities, but simplify also our calculations. So it is convenient and to work in the world of communications. dBs are the most common way to represent things. So we derived before this formula expressing the received power as a matter of EIRP on the transmit side, of receiving gain, and of free space path loss. Let's now express everything in dBs. So the receiving power P sub r in dB watts now is equal to the EIRP in dB watts, that we can express as 10 log base 10 of the product P sub t by G sub t, plus now, because it was a product, so logarithm of a product is sum of the factors G sub r, again in dBs, and dBs without dimensions, because gain is a ratio in itself, so it's dimensionless. 10 log sub 10 of 4 pi a sub b, equivalent area of the antenna, over lambda squared. And then eventually L sub p is the free space path loss, is a simplification, let's say, an abbreviation of the definition, equal 20 log 4 pi r over lambda. It's why 20, because if you remember, the free space path loss was 4 pi r over lambda squared. And again, because of the properties of logarithms, an exponent is multiplied, goes into multiplying the log. So I have the 10 log multiplied by 2, that is the exponent of the factor under logarithm, gives me 20. So L sub b equal 20 log sub 10 of 4 pi r over lambda. Again in dB, because it's a loss, like a gain. Gain and losses are similar, these are ratios, so are dimensionless. This equation, either in decibel format or in normal format, is very famous in communications, and it was defined by Friis, so it is called the Friis equation. It's a very important equation in the definition of a link, a communication link. Now let's make an example, just also to understand if we can in fact start handling these quantities to derive some useful information, and also to have an idea of the magnitudes of the parameters we are considering. In this slide, it is taken from leaflets of Eutelsat. I have the information about some satellites of the Eutelsat fleet, specifically the Hotbird satellites, that are satellites to broadcast television over Europe. And you see in the picture, in fact, what is called the ISO-IRP contour, or in fact a family of contours. What are they? Are the areas where the EIRP, as seen by a user coming from the satellite, is the same. A few definitions here. Why is the EIRP that we considered before depending on the position of the user? Because we said that the gain of an antenna is not the same in all directions. Here we see that the designer of the Eutelsat satellite tried to optimize the gain of the transmit antenna on board the satellite in such a way that the energy was focused over Europe. They wanted to get not only Europe, but basically Europe with some neighbor countries and areas. So they were optimizing this, but the gain is not exactly the same. And actually, if you try to optimize the gain over the center of Europe, it's obvious that the more you move away, and somehow the gain or directivity will fall down. And this is exactly shown here. The families of curves tells you that if you are in a Central Europe, you experience an EIRP, experience as seen by the user from the satellite of very high, in the order of 50 dB watt, to which it corresponds, this is an indication that is provided by Eutelsat, the possibility to use a receiving antenna of 60 centimeters in diameter. I should have said that we are speaking about Ku band frequency, so around 12 gigahertz. So the provider of the TV broadcasting service from satellite here, Eutelsat, tells you that if you use this satellite, this family of satellites, and you are in a certain area, for instance in the Central Europe, you have a good EIRP such that you can effectively limit the dimension of your receiving antenna to 60 centimeters. And then the more you move away, you see that there is a decrease in EIRP. This is nothing to do with the free space path loss. Here we are speaking about the fact that the directive gain of the transmit antenna is, of course, depends on the design of the antenna itself. We cannot get gain at all in all directions. If you get more gain in one direction, you have to experience less gain in another direction. This is, we said, I mean, the more you focus the energy, the lower will be the energy that you send to the rest of the free space. Otherwise, the antenna would create energy, and this cannot be. Fine, so this, let's use this information to make some calculation on a practical example. So in this slide here, just to start touching and using real numbers into our equations, I have just considered the case that we have seen before of a specific satellite with working at Ku band, so to simplify, we say 12 gigahertz, and delivering to my position, and my position could be Sofia, since we are filming this video in Sofia. Let's suppose it is Sofia. Sofia is inside the best contour, the one where the user experiences 50 dB watt. So let's assume that the EIRP from the satellite is 50 dB watt. Fine. Then also let's consider that the user in Sofia, knowing that and following the suggestion of the service provider, has indeed adopted a receiving antenna with a diameter of 60 centimeters. Now, quick and dirty calculation, let's assume that the efficiency of the antenna is around 60%, which is a rather conservative but not unlikely number. Then I derive and I know my frequency, 12 gigahertz, so I can derive with the previous formulas the gain of my receiving antenna. And I get something close to 35 dBs. So this is now my G sub r. EIRP is defined. To simplify the calculation, I consider that I am close to the sub-satellite point, which is not exactly true, but let's assume that I am at 36,000 kilometers from the satellite itself. It is a geostationary satellite we are considering. So then again, with the formula of the free space path loss, I can derive what is the loss from the transmitter to my ground receiver, which is equal to minus 205 dBs. Now I apply the Friis formula in decibels, so I have P sub r in dB watt equal to EIRP in dB watt minus free space losses in dBs plus, you remember that I had to subtract the losses and add the gain of the receiving ground station, plus G sub r again in dBs dimensionless. So let's put the real number, 50, the EIRP, minus 205, the free space path loss, plus 35, that is the receiving antenna gain, and I get a result, minus 120 dB watt. I want to now transform this number from dB watt to real watts, linear watts. P sub r in watts is applying the formula to go back from logarithm to linear numbers, then is 10 to minus 120 over 10. So it is 10 to minus 12 watts. So in other words, 1 picowatt. It's very, very, very small number. It's a very, very small power we are considering here. 10 to minus 12 means 1/1,000,000 of a millionth of watt. This is the type of, in fact, this number is even optimistic. Why? Because we have not considered many other losses that would add. For instance, we have not considered the atmospheric attenuation. We'll speak about it in a minute. We have not considered other losses deriving from the difference in polarization, error in the polarization that we have not considered, and you can maybe get some more information from the course on antennas. So this number is even optimistic, and still it is very, 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 very small. So when we consider a satellite link budget, we have to get acquainted with received power levels that are very, very small. And this is somehow also challenging. It means that we have to design our receiving stations with characteristics that are not trivial. And on the other side, we need to have the maximum power transmitted to compensate for the huge losses experienced by our electromagnetic signal traveling in space, in free space.